Assalamu alaikum students, and this is Talha Akram, and in this lecture we shall discuss clippers. In the previous two lectures we have discussed half wave and full wave rectifiers. The half wave rectifier is an example of simplest form of diode clipper, where we just have one resistor and a diode which are connected in a series. There are a variety of diode networks called clippers that have the ability to clip off or truncate a portion of the input signal without distorting the remaining part of the alternating waveform. The waveform can be a sine signal or can be a square wave or triangular wave. So depending on the orientation of the diode in the clippers, the positive or the negative region of the input signal is mostly clipped off. Here we can see clippers are networks that employ diodes to clip away a portion of input signal, which we just discussed. In general, there are two categories of clippers. One is series, in which the diode is in series with the load. Diode is in series with the load, like in this figure, figure A, and the diode is in series with the load because we are getting the output from this resistor R, and the diode is in series with the resistor R. For the second type of clippers, diode, which is called parallel clipper, diode is in parallel with the load. So diode is in parallel with the load. Load is V0. So here you just saw that for a positive half cycle, in case of series clipper, for a positive half cycle the diode will be in its on state, whereas for the negative half cycle the diode is in the off state. Same applies here. For the positive half cycle, diode will be forward biased, but for the negative half cycle means this will be positive and this will be a negative signal. So diode is in the reverse biased. So it depends on the network that the positive signal will be clipped or the negative signal will be clipped. So first we need to discuss the series clipper. In case of series clipper, we'll get the output V0 across from the resistor R. So the drop will be here. We can find out the drop at this point, positive one, in reference with the ground potential, which is 0 volt. So just an example, we have a square wave with the magnitude of plus V and a lower magnitude of minus V. So this is the output of this square wave. For the positive half cycle, you can easily observe that for the positive half cycle diode will be in its on state, whereas for the negative half cycle diode will be in its off state. So here for the negative half cycle the total current is equal to 0. This is for the negative half cycle. So this is the output, where we can see that for the positive half cycle we are getting the input signal and the output signal both are having the same magnitude, V and V, because in this case we are dealing with the ideal diode. Ideal diode means drop there will be no drop of 0.3 or 0.7. So at potential 0 diode will be in its on state. Same applies here for the other signal, which is a triangular wave. For the positive half cycle, diode will be in its on state, whereas for the negative half cycle it will be 0. One can observe this 0 for the time period, let t by 2. Let this is t by 2, this is t, and for the wave t by 2 to t, we are getting the output 0 volts. So the vertical magnitude, the vertical scale is voltage. So here we are getting the 0 volts here, and we are also getting the 0 volt here. In general, there is no procedure for analyzing Clipper networks, but there are something one can possibly do to give the analysis some positive direction. So here is a signal. This is a sinusoidal signal with the magnitude of Vm. Definitely it will be minus Vm. So total time period is t, and the half cycle is covered in t by 2, and the second half, the lower lobe, is in the time period of t by 2 to t. So what we can possibly do to analyze a circuit, first we need to take careful note of where the output voltage is defined. Here in this case the output voltage is defined across the resistor R. This is definitely a series clipper. So first case, we already identified where the output voltage is defined. The output voltage is defined at the voltage V0. As a second step, we need to make a mental sketch of the response of the network based on the direction of the diode and the applied voltage level. Means we need to try to develop an overall sense of response by simply noting the pressure established by each supply. Means here in this case, for the positive half cycle, the diode will turn on, but there is one condition which need to be met. So for the negative half cycle, diode will be in its off state. So we are getting an overall sense of response that for the positive half cycle we'll get some signal. What the signal will be, we'll take a careful note of that in the next 3 points. So we are getting an impression that for the positive half cycle we'll get something, and for the negative half cycle we are not getting anything. Okay. Determine the applied voltage that will result in a change of state of for the diode from the off state to the on state. So here you can easily observe that for the positive half cycle, where the polarity is positive here, the polarity is negative here, the diode is ideal diode, means we must get at least 0 volts. At least we need 0 volts here, so that diode will be in its on state, or the diode will be in the forward biased condition state. So here you can see, let Vi is in the range of 1 to 5. So when Vi is 1 volt, and let V is equal to, let 5 volts. This is 5 volts, and Vi is in the range of 1 to 5 volt. For Vi is equal to 1 volt, pressure will be applied here, and here we'll lose the pressure of 5 volts. So the output voltage here will be minus 4 volts, and the diode will be in its off state. When Vi is 2 volts, so 2 minus 5, here we will get minus 3 volts, diode will be in its off state. When Vi is equal to 3 volts, then 3 minus 5 is minus 2 volts, and the diode is still in its off state. When Vi is equal to 5, V is equal to 5, so Vi minus V, this is what we'll get here at point at the output terminal V naught. So 5 minus 5 will be 0 volts, and the diode will be in its condition that it will allow the current to pass through. So we are getting potential 0 volt, but the diode will be in its on state. Same thing applies here, like minus V, here we are getting a drop when Vd is equal to 0 volt. Means the potential applied on the diode is 0 volt, then it will allow the current, and the current will flow here. And the because in this case potential is 0, so output there is no the current will not flow through it, but diode will be in its on state. So V naught is equal to 0 into R is equal to 0 volt. Drop will be 0 volt, but this is connected now. So we must need to take care of the applied potential and the battery which is connected in series with it. So if the terminals if we make the terminal reverse, then what will happen? This will be a positive negative terminal, and this will be a positive terminal. So what the input voltage is, let Vi is equal to 0 volt, then V is equal to 5 volt, so output potential will be 5 volt. The waveform will start at the potential, will start from the potential 5. So coming to the next point, it is often helpful to draw the output waveform directly below the applied potential using the same scale. This is what we discussed lately. So this is what we have done earlier, that output potential is equal to input minus drop, which is V. If we reverse the battery, then it will be Vi plus V. So output potential, there is no drop here. In case of silicon, the drop will be 0.7 volt or 0.3 volts. So here in this case, when the diode is ideal, V naught will be, in this case, Vi drop is equal to V naught. We just applied the KVL here, so V naught is equal to 0 volt if they both are same. So when the let V is equal to 6 volts and Vi is equal to 7 volts. So 7 volt will be applied here minus drop, so output will be 1 volt. Just put the values here in this equation. Vi is equal to 7 and V is equal to 6, so output will be 1 volt. We will get a signal of 1 volt here. And if the battery is reversed, then it will be like this, minus and positive. So let Vi is equal to 7 volt and this is plus 6, so V naught is equal to Vi plus V. So V naught is equal to Vi plus rise of potential, rise and drop. So you can also apply the KVL using the sign convention. Minus Vi minus V plus VR is equal to 0, so VR is equal to Vi plus V. So VR or V naught, so V naught is equal to Vi plus V if the potential battery potentials are minus here, terminals are reversed basically. So V naught is equal to Vi plus V. Now this is what we just discussed, that the battery potentials are opposite. Uh, Here the battery potentials are plus minus, here the battery potentials are minus plus. So it seems that whatever the input voltage is, we'll be getting a positive 5 at the output V naught. So Vi is equal to 0, we'll get positive 5. When Vi is equal to 1, we'll getting 1 plus 5 is equal to 6. So let's see what we can possibly do. Now, following the steps which we just have discussed, first we need to identify where we are getting the output. So the output is again directly across the resistor R, and the diode is in series with the resistor R. So we are getting the output here at point V naught. Now, as a step 2, the positive region of Vi and the DC supply both are applying pressure to turn on the diode. For the positive half cycle, diode will be on, whereas for the negative half cycle, diode will be in its off state. But there is something different here in this question, because when we'll apply 0 volts in its reverse direction, diode is getting a positive signal from here due to this potential V. So it will give something here. So we'll discuss it in this example. So it is also written, it would have to exceed the DC supply voltage of 5 volt before it could turn the diode off. This is what we discussed, and it's in the negative half cycle from T by 2 to T. So in the step 3, the transition model is substituted in the figure 2.75. This is actually 2.75, and we find out that the transition from one state to the other will occur when Vi plus 5 is equal to V naught, and here what we are getting, because there is a step up voltage of 5 volts, so we are getting here Vi plus 5 is equal to 0 volt, or this is the point where we'll get the 0 volt when the applied potential is minus 5 volt. So let me discuss this thing again. This is the point that at this voltage we'll get some signal over here, means across the resistor R. When you'll apply minus 5 volt, we already have a step up voltage of 5 volts, so we'll get something. So here we are getting minus 5 volt at we'll get something at the resistor R. It will start at minus 5 volt. So Vi plus 5 volt is equal to 0 volts. So we are getting 0 volts here when the applied potential is minus 5. When the applied potential is minus 4, we'll getting something. Definitely we'll get at least 1 volt, because minus 4 plus 5 is equal to plus 1. So for the voltage less than minus 5 volt, the diode is in its open circuit state or off state, and the output potential will be 0 volts. So V naught is equal to Vi plus 5. This is what we are getting here. This one. Minus Vi minus 5 plus V naught is equal to 0. Minus Vi minus V plus V naught is equal to 0. This is KVL. So V naught is equal to Vi plus V. So this is what we are getting here. V naught is equal to Vi plus V, because V is 5 volts, so V naught is equal to Vi plus 5. So let's see what we got here in the output signal. We have a potential of 0 volt up to maximum magnitude of 20 volts. So uh, coming here, when Vi is 0 volts, when Vi applied potential is 0 volt, we are getting an output of plus 5. So when the input signal is 0 volts, output is 5 volt. When the input value is 1 volt, like we are, for example, we are here, then the output signal will be 6 volt. When the Vi is here, let at 2 volts, the output signal is V naught is equal to 2 plus 5 is equal to 7. This is 7. So when Vi is equal to 20 volts, when Vi is equal to 20 volts, the output will be 20 plus 5 is equal to 25. This is what we are getting the peak. When the input is 0, we are getting 5 volts. When the input is 20, we are getting 25. So when it is decreasing, let Vi is 10 here. So we are getting somewhere 15 here. So here at this point, when input signal Vi is 0 again, we are getting something plus 5 volts here. So the positive half cycle starts from here and ends here, and this is the difference which is created by a potential V. This is a difference which is created by a potential V. So coming to the negative half cycle, it's quite tricky here, that when the input signal is, for example, minus 1 volts. So here in this case, this is plus, this is minus. When we have applied 1 volt here, this is 1 volt we'll apply here. The potential here is positive 1 and positive 5. So in this case, the difference will be 4 volts. So when we have minus 1 here, we are getting the potential positive 4. Just apply the value here. V naught is equal to minus 1 plus 5. It's positive 4. When Vi is equal to, let minus 2 at this point, minus 2 plus 5, the output will be here somewhere 3. Negative half cycle already started. When Vi is equal to minus 4, maybe we are here somewhere, then the output will be positive 1. When Vi is equal to minus 5, the output will be 0. So here, when it is minus 5, input signal is minus 5, the output signal is 0. And when the input signal is minus 20, then the output is when the input signal is minus 20, it is minus 20 plus 5, the output is 0 volts because diodes in its off state. So now coming to this point, when Vi is equal to minus 5, again the output is 0. We are here. When the input is minus 4, the output will be here plus 1. Then when the input is minus 1, the output will be here somewhere positive 4. When the input is 0, the output will be positive 5. So one complete cycle ends here at this point. So this difference is created by, and this as well, basically this as well, this is created by a potential V here. So coming to the equations, Vi is equal to 5, Vi plus 5 is equal to 20, input plus 5 is equal to 20. So total voltage is Vi is 20 plus 5, 25, the output potential is 25. So V naught is equal to 25. So when the V naught is -5, the output will be 0 volts. This is what we discussed just now.